So I posted the quick surveys in the Blackboard. Okay, so then around the 40 students respond. So if you read the survey question, then you can find that. So actually in this course, you need some knowledge about the Linux operating systems, virtual machines, then also the HDL, the hardware description languages. Then so so in this course, around the 40, 78 students registered for this course. Then 41, I believe around the 1/3 of students are not familiar with the Linux operating systems, system Verilog, and then some tools such as the virtual machines. Actually, your virtual machine, so it's small. Okay, but actually we don't have enough time for teaching some these how to use these tools. Okay, so I recommend you to study by yourself the usage of these tools. So if you are not familiar with the Linux operating systems, then you can just Google. You can just Google some Linux commands. Also actually in the first lab, I will explain how to install how actually I will provide, I will not explain. I will provide some instructions about how to install Linux operating systems on virtual machine. Okay, so you can follow the instructions, but you can also you need to practice. Okay, you need to practice some commands. Also, you can uh, practice how to use this Linux operating systems. Okay. Also, if you are not familiar with how to use these tools, you can get help from PA. Okay, you can visit PA's office by appointment. Sorry. So try to get help from PAs. Okay. So as I mentioned, we don't have enough time for teaching how to use these tools. Okay. Also, I found that around the 1/3 of students did not take the digital logic design course. Uh, Actually, the knowledge on digital design is required for performing the design tasks. Okay, so I will post the lecture videos, lecture videos of this digital design, digital system design course. So actually, you can just watch some several videos regarding the system value part. Okay, so we will use system value, okay, for design apps. So I'll post some links for the system value part of the last semester, the previous semester. So you can watch YouTube videos. Okay. Okay. So um, then if you see the blackboard, you can find the left lane, left pane, left panel. Okay. Left panel here, and then if you click the resources and Piazza, so it's not connected. Okay, I think it's not connected because it's from from Hmm. Internet speed is so slow here. It takes long. So, okay, so, oh, here. I think it's so slow, okay? So, so, so I mentioned that in the first class, I will post the recorded lectures on YouTube, right? So you can watch YouTube lectures for reviewing the lectures. So also, so this is the in-person lecture, okay? So you need to attend the lectures or classes, okay? It's important. Okay, okay. Oh, so if we check the resources tab, uh, hmm, so, oh, oh, you can find the links to the lecture videos on the Piazza. Okay, so usually I include the recorded video during the weekend. Okay, so and then I will post the links to the YouTube video here. Okay, and you can watch the videos. Okay. Also, please read the syllabus if you first attend this course. I believe some students registered for this course after some register change period. So please read the syllabus. Okay. So and then uh, and then so it's important. You need to check your attendance by yourself. So using the self attendance check link right here. Okay. So I will not check your attendance manually, as I mentioned. So please check your attendance by yourself. Okay. So any questions? So how will change? So what did we learn in the previous class? Do you remember? We learned about the abstraction of the computer systems, right? So what is the meaning of abstraction? So I mentioned that you need to understand the concept of abstraction. Okay, so hiding details when they aren't important, right? So we can just understand some interfaces. So if we just focus on a certain layer, so I explained that the computer systems are composed of many layers, right? So like the program layers, device, operating systems, architecture, microarchitecture, and then some logics and hardware design. So because the computer system is a very complex system, we can just understand a certain layer, right? So we can just focus on certain layer, okay? Then we, in this case, we can ignore unimportant things, okay? So if we just focus on the some microarchitecture level here, then actually some knowledge on logic and digital circuits can be unimportant. So you can just ignore some knowledge on digital circuits to understand the knowledge on microarchitecture. Okay, so you can just ignore because it's very complex. But we can just understand some interfaces between layers. This is a concept of abstraction. So we frequently use this concept of abstraction in our real life. Okay, okay, so then I briefly explain about the organization of a computer system and the, the technology below our computer system, like semiconductor technology. Okay, as I mentioned, semiconductor technology is very critical, right? Because actually the performance and the cost of a computer system is usually determined by the semiconductor technology. So it relies on semiconductor technology. Okay, it's so important. So the semiconductor technology is so important for the nation's industry, right? Okay, so that's what we learned in the previous class. So, so in this time, we will learn about the performance of a computer system. So I briefly showed the analogy of performance for airplanes. Okay, then how can we measure or how can we compare? I mentioned that how can we measure, but I mentioned also how can we compare? How can we compare the performance? Actually, enough to measure, so I frequently use measure or compare, but actually we need to compare the performance of a certain computer system with the performance of baseline or other computer system. Okay, that's how we measure the performance of a target computer system. So you need to remember this. We can compare. We can compare the performance of a computer system. So in the analogy of this airplane performance, I mentioned that we can use different types of performance metrics such as speed, the latency, the execution time, the flight time, or capacity. So we can use different types of performance metrics. So it's the same for the computer systems. In order to measure the computer system, that we can use two different types of performance metrics. So these are two representative performance metrics in computer systems. Okay. The first one is response time, and then the second one is throughput. So you need to understand the meaning of these performance metrics, such as the response time and throughput. Then, what is response time? What is the meaning of response time? So we can say that this is also execution time. Okay. Okay. Or it can be called the latency. Okay. Now what is the latency? So response time or execution time or latency, it means how long it takes to do a task. Okay. So response time, now we can measure the response time, like some time gap between the start time and the end time of a certain task. Obviously, right? So like this, we want to measure some response time of our 100-meter race. Okay, then we can just check the start time, and then at the goal of the 100-meter race, so we can measure the end time. Okay, then we can measure the response time of our 100-meter race. Right, so it's the same. The 100-meter race is a kind of a task. But so we can measure the response time of our 100-meter race. So 100-meter race is a track, okay? And then you can just measure the start time and the end time, and then the time gap between the start time and end time is the response time. So by measuring this response time, we can compare the performance, right? So for example, in the 100-meter race, we can compare the performance of the person A and person B, right? So this is the response time, the definition of response time. So, and then what is the second performance metric? It's throughput. Throughput is also frequently used performance metric in a system, right? So what is the definition? Definition of a throughput is total work done per unit time. So in order to measure the throughput of a system, we can measure the amount of work done during a unit time. For example, if a computer system processes a certain data, then we can measure the amount of data processed during the unit time. So for example, 100 megabyte of data per second. So this is the example of throughput. So we can also measure the amount of work done per unit time during the unit time. Okay. So if we just focus on a certain task, we can measure the response time. If we just focus on the amount of work, then we can measure the throughput. Okay. So you need to understand the definition. This definition of two terminology, response time and throughput. Sometimes we can focus on the response time. What case? Okay. So if we just focus on performance of a single task, we can use the response time, right? I mentioned we can just compare the performance of a single task, right? A single task. Then we can use response time or the performance metric. But if we just measure the amount of work done by a certain system, then we can use throughput. Okay. So based on some target purpose or some target of the system, that we can use the different types of performance metrics. Okay. So for this course, we will focus on the response time. So recently we frequently use the throughput because recently we frequently use parallel application. But this is the basic course of computer architecture. So firstly, we need to understand how to measure the performance of a single task or single thread. Okay. So we will focus on the response time now. Okay. So then how can you measure the performance? How can you measure the performance of a certain system? So I also mentioned that we can compare the performance of a certain system. So for example, so person A and person B, so they are they are racing on the 100-meter race. So how can you measure the performance? So how can we compare the performance of person A and person B? We can just measure the response time, like the time gap between the start time and the time. Then how can you compare how can I say a performance of A is higher than performance B by x dot x percent? So, so sometimes we need to compare, right? Because when we purchase a certain system, then we can just compare the performance, right? The performance of system A is higher than the performance of system B. So based on this fact, we can purchase a certain system, right? So sometimes we, we frequently compare the performance of two systems to measure the performance, right? Then how can you compare? So I mentioned that the performance A of a certain system or a person A is higher than the performance of B by XXX%. That is the default comparison, the default method or default approach to compare the performance. So we can find that is, so we can compare the performance of a system X and then over the performance of a system Y. How can you compare? We can just divide the performance of a system X by divide by performance of system Y. Okay. Then we can say that, oh, if this is larger than 1, then X is n times faster than Y. Okay. So if this is n, you can say that the X is n times faster than Y. Right. Then how can you compare the performance? So I mentioned that we can measure the response time of a certain task. But if the response time is high, it means the performance is low. Right. So think about the 100-meter race. If the response time is high, so like the 20 seconds, then the performance is actually low. So if you compare the response time 10 seconds or 20 seconds for the 100-meter race, then the performance of 10 seconds is higher than the performance of 20 seconds, right? Obviously. So what can you find? Actually, the performance of a system is proportional to the inverse of response time. Okay, so we can measure the response time of a certain task, but actually the performance is inversely proportional to the response time. Obviously, right? So I mentioned that we can say like this, X is n times faster than Y, then we can just compare the performance. The performance of X divided by performance of Y. But actually, this equation is equivalent to the execution time of Y divided by execution time of X, right? So because the performance is inversely proportional to the execution time. So this equation is the basic equation. Okay, if we understand the basic equation of a certain system, then it's okay. It's okay. So just to remember how to measure the performance of system A and system B. We can measure the performance of our target system by comparing the performance of two systems. Okay, so this is the example. So time taken to run a program, so a single task. right, of a single program. So it takes us 10 seconds on computer A, and it takes us 15 seconds on computer B. Then how can you measure? So we can just measure the performance like top A, the by definition, divided by top B, and then this is the inverse of the response time. So this is the time B divided by time A. So it's simple, right? It's 15 divided by 10, so 1.5. Okay, so this is the final answer. A is 1.5 times faster than B. Okay, so actually, in a midterm exam, also in the homework assignment, so you will be asked like the compare the performance of A and B. Then you need to answer like performance of A is XX faster, XX time faster than performance of Y. Okay. Okay. So during in the exam or in a homework assignment, you need to answer like A is X times faster than B. Okay. Based on this equation. Okay. So it's very simple. So how can we measure the performance? Well, we can measure the response time on a certain system. It's very easy, right? And then, well, actually, the real situation is not simple. So actually, I mentioned that our computer system is a very complex system. Also, our computer system is composed of many layers. So the response time of a certain program is also influenced by many factors. So for example, our application, so applications run on operating system, right? Like the Windows, Linux operating systems, or Mac OS, Android. So actually, the response time of a certain application is influenced by operating systems. Also, sometimes so we run many applications concurrently, so in parallel. So actually, so in a computer system, so the response time of a certain application is influenced by operating systems, and then input and output devices such as keyboard, mice, and network. Also, other processes or other threads such as other applications. Okay, so it's not easy. So it's not easy to measure the response time of a single task in a complex system. So when you measure, when you mention of a response time or the performance of a single application, then it just it means CPU time. Okay, so it's actually the response time, the real elapsed time is influenced by many factors. So we just focus on the CPU time. Then what is the CPU time? All these factors are removed. So we assume that a single application or a single thread or a single process runs on a CPU, and so only one application runs on a CPU. So this is the CPU time. So the influences from operating system is removed. IO part is also removed. Also, the interference from other applications are also removed. So we assume only one application or one thread, okay, one program runs on a CPU. Okay, this is the CPU time. So in order to measure the performance of a CPU, then actually we need to measure the CPU time. So we will consider only a CPU time. Okay. Okay. Then okay. So in order to understand the performance of a CPU, then also you need to also understand how these the systems work. So if you took the system design, previous semester, then I believe you know how the systems work. Okay. So actually, a CPU, the processors are part of a digital system. It's a kind of digital systems, and not in order to run a digital system or digital logic, then we require a clock signal. It's a clock signal. Why? So it is because the digital system is composed of synchronous part, synchronous logic, and the combinational logic. This is the combinational logic, and then this is the synchronous logic. Okay, and then actually the synchronous logic is working based on the clock edges. So which means that the data from this combinational logic is sampled at the rising edge or falling edge of the clock signal. Okay. So actually, so you need to understand the clocking, the clock signal. So then what is the clock signal? And then why clock signal is critical, so important for the performance of CPU. Okay. So I believe if you are interested in the performance of your smartphone or laptop or your desktop, then you can compare the specification of CPU, right? So if you want to buy a new smartphone, then you can compare. So you want to buy a higher performance one, right? Then you can compare. So usually we can compare the clock frequency. Frequency of CPU, right? So let us assume that my current smartphone works with the 2 gigahertz of CPU clock frequency. Then I want to buy a new smartphone. Then I want to buy I want to increase the performance of my smartphone. Then I can just compare the clock frequency. Then I can if the clock frequency is higher than the old one, then I may purchase that smartphone. Okay. So we frequently compare the clock frequency. That is also called the clock weight. Now, what's clock frequency? So this is the waveform of the clock signal. The clock signal is the repeated signal. Then actually the value of clock signal is repeatedly changed from 1 to 0, 1 to 0, or 1 to 0. So clock signals A clock signal is the repeated signal. So, and then the value 1 and 0 are repeatedly changing, and then periodically. Okay. So what does that mean? So one mean actually, this is the system. One is the high voltage, okay, high voltage, and then 0 is the low voltage. But anyway, the signal value 1 and 0 is repeatedly changing, and then periodically. So this is the clock signal, and then this is the periodic signal. Then we can define the period and frequency. So what is the period of this clock signal? Period is the time between a certain rising edge to the next rising edge. This is the period of clock signal, and then it's called the usually PC. Okay, PC. C means the clock. So this is the clock period. Then what is the frequency? Frequency is the inverse of period. So we frequently use the F for the frequency. F is the 1 over PC. So frequency represents the number of clock periods. So this is called this amount of time. This is called the cycle. So this is the actually one cycle of a clock. Okay. So frequency represents the number of clock cycles per unit time. So then what does that mean? What is the 2 gigahertz? The clock frequency is the 2 gigahertz. What does that mean? It means there are 2 multiplied 10 to the power of 9 cycles, clock cycles per second. So we can count the clock cycles per unit time. Then we can count 2 multiplied by 10 to the 9 cycles, 2 gigacycles per unit time. This is the meaning of clock frequency. So I mentioned that this is the clock cycle. So it means that we can count this amount of clock cycles per unit time. And why? Why is this clock signal critical for the performance? So it is because it's just assumption, but we just assume that a CPU or processor can perform on a single instruction per clock cycle. So what does that mean? So actually, so in the previous class, we learned that the high-level language code is translated into the assembly code. Then this assembly code is also translated into the machine code. So it means actually a program includes the many instructions. So instruction is, so we learn about the instruction. So many instructions. So actually, now to run a program, the CPU execute many instructions generate from a program. Okay. So if a CPU can execute more instructions per unit time, we can say that obviously, the performance of CPU is high. right? So a program has this amount of work, but and then CPU can execute any instruction, more instructions, then we can reduce the response time, right? So and then usually it's not true, but usually we assume a CPU can execute one instruction per clock cycle. Usually, I mentioned usually. Okay. So what does that mean? If the clock frequency is high, so it means there are more clock cycles per unit time. It means CPU can execute more instructions. Do you understand? Okay. So clock frequency is critical. Okay. So it's just assumption, and I mentioned that this is not true. Okay, this is just not true. But if the clock frequency is high, then we can expect that a CPU can execute more instructions per unit time. Okay, that's why the clock frequency is critical for the performance of CPU. Okay. So this is the definition of a clock cycle or clock signal. And then this is important. So you need to understand the definition of a clock cycle or clock frequency. So this is because during this course, so we will frequently use clock cycles. So how many clock cycles or clock frequency? Okay. So try to understand this. So the clock period is the duration of a clock cycle. So this is the clock cycle, one clock cycle. Okay. Then clock frequency is the inverse of clock period. Okay. Then how can you measure the CPU time? So I mentioned that we need to measure the CPU time of a certain application to measure the performance, right? Then how can we measure the CPU time? Okay. So we learned about the clock signal. Okay. And the CPU works with a clock signal, right? Then how can you measure? So it's simple. So we can just measure the number of clock cycles. So number of clock cycles for running a certain application. Okay, and multiplied by clock period. Clock cycle time is clock period. Okay, then we can measure the clock time. The unit is second. Okay. Then we can say that the number of clock cycles is divided by clock rate. Okay. This is the CPU time. Then how can we increase the performance? So this is the definition. So why definition is important? Why equation is important? So it is because if we see the equation, then we can find out which factor needs to be improved. Right? So the CPU time. The CPU time is defined as the CPU clock cycle, number of CPU clock cycles divided by clock rate. Okay, and then in order to increase the performance, we need to reduce the CPU time, right? Because the response time is the performance is the inverse of response time. So how can you reduce the CPU time? we can reduce the clock cycles, right? clock cycles for running on an application, or we can increase the clock rate. Clock rate is the clock frequency. So you can understand. So if you study this equation, you can understand why clock frequency is important, and then why people compare clock frequency to compare the performance of computer systems. Is it because clock rate is here, and then the CPU time is inversely proportional to the clock rate. Okay, so it means performance is proportional to the clock rate, clock frequency. Okay, so this is the CPU time. So this is the example. So computer A works with the 2 gigahertz of clock signal, and then it exhibits 10 seconds of CPU time. And then we want to design computer B. So the goal of this computer B is the 6 seconds of CPU time. But we can use the faster clock, but the number of clock cycles is increased. Okay? Then how can we set the clock frequency of this computer B? So in order to achieve 6 seconds of CPU time. So we can use the actually this equation, right? So if we use this equation, then we can just calculate actually the clock cycles for this program in the computer A, and then actually the clock cycles are increased by 1.2, okay, 1.2 times. So if we know the clock cycles of this application on computer B, and if the CPU time is 6 seconds, then we can get the clock rate. Okay. So because this equation is very simple, then we can just read the this part. Okay. So we can make the problem like this, but it's very simple. Okay. So actually we can rewrite the CPU time equation. So it is because how can we measure the clock cycles? Actually, we can define the clock cycles of a certain application. The instruction count multiplied by cycles per instruction. So cycles per instruction is called CPI, so cycles per instruction. So we can rewrite, we can define a new equation like clock cycles is the instruction count multiplied by cycles per instruction, CPI. So if we use this equation, then we can also define the CPU time is the instruction count multiplied by CPI multiplied by clock cycle time, clock period. So actually this equation is very important. Okay. Okay, I will explain about the instruction count. So let us assume that this is the application A, okay? And then application A needs to be compiled. to be run on the computer system. And then I mentioned that if an application is compiled, many instructions are generated. Okay, like add, multiply, and solve. So actually, so many instructions are generated. Okay, okay, it's a compiled, and then it's a compiled instruction. Here we can count number of instructions in an application A after compilation, right? So this is the instruction count. And actually, when an instruction is executed by a processor takes different number of cycles. So that's why I mentioned, oh, you assume one instruction is executed per clock, but it's not true. Okay, we just assume. Actually, when an instruction is executed by a processor takes different number of cycles. So it is because a certain instruction is complex, but a certain instruction is simple. Okay, so a CPU takes different number of cycles per instruction. So that's why we mentioned the cycles per instruction. This is the average number of cycles per instruction. Okay, so you can define the clock cycles. The clock cycles for running application like the instruction count multiplied by CPI. Okay. So the CPU time is the number of cycles multiplied by clock period TC. So this part is replaced by instruction count. Oops. Instruction count multiplied by CPI, clock per instruction. So we can rewrite the CPU time equation like CPU time is equal to instruction count multiplied by CPI multiplied by TC. Okay. So this is the basic equation for measuring CPU time. This is important. So you need to memorize. You need to memorize this equation. IC multiplied by CPI multiplied by TC. The basic equation for measuring response time or CPU time. Okay, and then right. So and then I explain about the IC multiplied by CPI. So then why do we need to rewrite the equation like this? This is because it's useful for analyzing system. Okay, and then we can figure out which factors need to be improved for performance of our computer system. So we can figure out by analyzing this equation. How can we increase the performance? So you need to understand that. So in order to increase the performance, we need to reduce the response time, obviously, right? So how can we reduce the response time? We can reduce the instruction count, or we can reduce the CPI, or we can reduce the clock period, right? And so actually, in a computer system, this part, the instruction count, this part, and CPI, and then it, PC. So these vectors are influenced by different components. So for example, so if we see that this equation, we can know that in order to increase the performance, we need to reduce the instruction count of our application. And how? We need to make a good code, right? It means we need to apply better algorithm. That's why we need to learn algorithm, the computer science or computer engineering. So instruction count. Instruction count is influenced by algorithms in an application. Okay. So we need to apply efficient algorithm in our code. Okay. So this is the instruction count is the software part. How about the CPI? It's the clock per instruction. It means the average number of clocks taken by instruction, a single instruction. Okay? It depends on architecture, the microarchitecture, instruction set architecture, such as the x86 or ARM. Also, this part is influenced by compiler. Okay? And then clock period. Clock period is influenced by hardware design and semiconductor technology. Okay, so in a previous class I mentioned that if we make smaller transistor, then we can increase the performance. So it means that a transistor works faster. So if we make faster transistor, then we can reduce the clock period. Okay, so clock period. So if we analyze this equation, then we can also figure out which factors need to be improved for increasing the performance. Okay. So this is the example. So we can read this example. Okay, it's just an example. Then, but CPI. So let's see about the CPI. Okay. So I mentioned that clock per instruction. So the number of clocks taken by instruction is different. So which means we want calculate the average CPI actually. Okay, so average CPI. But there are different types of instructions in an application. So for example, actually we can classify instructions such as the arithmetic integer instruction, or arithmetic floating point instructions, or data transfer instructions such as load, store. Also, we can classify instructions like branch instructions. So, okay, so we will learn about this type of instruction in chapter 2, but you can just know that there are different types of instructions. And then the proportion of these types of instructions is also different. Right. So this is our code A and then code B. If the code is different, so it means that the software or application is different. Applications exhibit different proportions of these types of instructions. Obviously, right? So we can use many floating point instructions for application A or for the application B. We can use the many integer instructions by the purpose of our application. So, which means actually the CPI, the clock for this instruction is different. So usually the floating point take longer cycles. Floating point instructions take longer cycles because the floating point is more complex. Okay? So what does that mean? Actually, the CPI is also different by different applications. So it is because the proportions of instruction type is also different. You understand? Okay. So actually, in order to calculate the CPU time, the instruction count and CPI and TC, instruction count and then CPI and TC, okay? Then actually we use the average CPI, but in order to calculate the average CPI, then we also need to consider the proportions of instruction types. Okay? Then let's see how. So we need to calculate the average CPI like this. So let's see the example. Okay. So this table shows the instruction types A, B, and C. And then we can find the CPI for the instruction types. So CPI for instruction type A is 1. It means that the processor takes 1 cycle for this instruction type A. And then CPI for instruction type of B is just 2. And then this is 3. Okay. So CPI is also different by different type of instructions. So I mentioned, okay. And then the sequence 1 is application 1. Okay, it's application 1. And then this is the application 2. And then as I mentioned, applications, different applications exhibit different proportion of instruction types. So as you can see in this table. So in the sequence 1, it's application A1 has the 2 instruction A, 1 instruction B, and then 2 instruction C. Then how can we calculate the average CPI? It's simple, right? Because what is the CPI? CPI is the clock cycles per instruction, right? Then in order to calculate the CPI, firstly, we can calculate the total number of clock cycles, and we can calculate the number of instructions, and then this total number of clock cycles is divided by number of instructions. Why? Because this is the just definition of CPI. Okay, then A1 has the 5. A1 has 5 instructions. What happened? 5 instructions. And then how about the A2? A2 has 6 instructions. And how many cycles? We can just multiply number of cycles by instruction time. Okay, how many cycles? So 2 multiplied by 1, 1 multiplied by 2, 2 multiplied by 3, 10. This is the total number of clock cycles for application A1. What is the average CPI. Average CPI is the, by definition, 10 divided by 5 is 2. Equals 2 is the same, it's 1.5. So this slide shows that for the different applications, actually, average CPI is also different. Why? Because the proportion is different. So I'll post the first homework tomorrow. Okay? Then you can find the similar questions like this. Okay? Actually, the basic equation is very simple. In order to measure the CPU time, this is the instruction count multiplied by CPI multiplied by TC. But actually, because an application includes many different types of instruction, the CPI part, is actually not able to calculate the average CPI. We need to consider the proportions of instructions. Okay. So this is summary. Okay. So this equation is very important in this course. Okay. Because actually the purpose of computer architecture is to build better computer systems. It means high performance computer systems. And then, as I mentioned, these factors are influenced by different components. The algorithm, programming language, compiler, and then instruction set architecture or hardware. So if you see this part, then you can find some course names in computer science department, computer engineering department, right? Compiler, algorithm, and programming languages, then architecture. Okay, because these factors are critical for the performance of computer system. Okay. Okay, so this is another example of performance metric, MIPS. So MIPS represent the millions of instructions per second. So if we just understand the definition of a performance metric, then we can calculate this performance metric. So MIPS represent actually millions of instructions per second. So actually, if we just ignore millions, MIPS is the number of instructions per second. Okay, so we can use MIPS for measuring the performance of computer systems also. Right. If we just see the definition of MIPS, then this is the number of instructions per second. Then intuitively, if a computer system execute more instructions, then we can say that this computer system exhibit higher performance, obviously, intuitively. Right. So we can say that if the MIPS, okay, if the MIPS value is higher, then the performance is also higher. But it's not always true. Okay? So I mentioned it's not always true. Why? Which part is missing? So actually, you need to understand. You need to remember that the basic performance equation. Okay, what is the base? So CPU time. The execution time is the instruction count multiplied by CPI multiplied by TC. Okay. But what is the MIPS? MIPS is the number of instructions per second. Number of instructions per second. So which part is missing in this equation? Actually, this part is missing. Okay, so if the instruction count is the same, right, then we can use MIPS as the performance metric to compare the performance, right? But actually, when you mention MIPS, this part is missing. Instruction count. So it means actually we cannot use MIPS for measuring the performance of two computer systems directly. So if this part, the instruction count part is the same, then we can use MIPS. We can use MIPS for comparing the performance. Okay, right, but because MIPS does not consider the instruction count part, we cannot use MIPS if this information is not provided. So for example, this is the same application A, and this application is compiled to different ISA, like this same application can be compiled using x86 ISA and then ARM ISA. Then instruction count is different. Okay? Instruction count. Because the instruction set architecture is different, then the generated the number of compiled instruction can be different. It's different. Okay. So maybe the MIPS of x86 is lower than the MIPS of ARM. That can be possible. Okay. But we cannot say that, ARM is faster than x86 in this case. It is because the instruction count can be different. So we will learn about the CISC type and RISC type CPU in chapter 2, but actually the x86 is the CISC type, the complex type CPU, and then ARM is the RISC type, the reduced type. It's a simple. Okay. So usually, I said usually, it's not always true. Usually, if the same application is compiled with RISC type instructions, then the generated number of generated instruction is large. Okay. So it means if the MIPS, even though the MIPS can be higher, but the performance can be low. So you need to understand this equation. So this is the basic equation. So actually, to compare the performance, we need to use this equation. So we need to measure the time, okay? Latency or response time, CPU time. So if all information, all vectors are not provided, then we cannot compare the performance correctly. Okay, so you need to remember this. Okay, so the MIPS question can be also appear in Python. Okay. Okay, so I'll stop here. Any questions? Okay. So thank you for your attention and see you in the next class. 감사합니다.